All right. I'm trying to make this video um, because ACI code has a bunch of really important information, but then not many pictures. So it is many times for people preparing for PE or the breadth AC exam, it becomes real hard to visualize what is being said in various sections. So I'm trying to see if I can add some pictures that can replace thousands of words. So let's talk about development length today. It's a random topic, but then we'll slowly start getting, if you people like it, we'll start slowly getting into different topics, and we'll not use any PowerPoint presentation or any other formal way of presenting all these things. We'll open the code because most of the times in the exam, that's what you have. So we have to get used to the code. So open the code, start scrolling through different sections and talk about it and draw pictures on the screen and see if we can make this a little bit better. So firstly, we are ACI 318, 2014 version. I want to talk about the development length of reinforcement, which is chapter number 25 here. It's under the reinforcement details. We'll not talk about every little detail here, just talk about information that is good enough for someone to sail through a PE or a SC breadth exam. And once you start visualization, you can start reading yourself and then figure out all the details. So what is development length? Let's say we have a column like this, and we have a beam teeing into the column. Because of the load on the beam is, let's say, forget about the direction of moments here. Let's say it is undergoing a moment in that direction. Now that moment is causing push and pull in the reinforcement. Let's say this reinforcement is getting pulled out of concrete. Let's say it's getting pulled out like that. If you don't provide, let's say here is the critical section, the dotted line is a critical section. If you don't provide sufficient development length on either sides of this critical section, then the bar will not develop its full yield strength, and before it develops its full yield strength, the bar can come out of or pull out of concrete. So it's not just good enough to provide a bar based on the moment, but then we'll also have to detail the reinforcement and provide a decent embedment length, if I can call it so. And that minimum value is called LD, and it depends upon a bunch of factors. So in this lecture or in this session, we'll just talk about what development length is. We'll quickly jump into that particular section and then go through the code there. 416 page number, that's where the development length information is provided. And you can see this is what I was trying to say. Tension or compression in reinforcement at each section of a member shall be developed on each side of the section. So if in the example that we had, let's say you have a beam like that, you have a moment. Let's say here is the critical section, the face of the support for moment, let us say. You have to provide the development not only in this direction, but also you have to provide it in the other direction. So both the directions, right? And now this applies for a hooked, a headed, deformed bar, or any other mechanical device, or a combination of these things, right? So let's go to the next section. Important information here. If you see, so this particular value here, as you can see, the FC square root of FC prime, this value here, square root of FC prime should not be greater than, should not exceed 100 psi, which means FC prime should not exceed 10,000 psi. Usually we have a 4,000 psi concrete, 5,000 psi concrete, but this is one. I mean, if you have a I don't know, I'm just trying to make it up. If you have a 12,000 or 16,000 psi concrete, then your upper limit, you still have to use it. For your FC prime value, you still have to use 10,000. So that is what this section says here. Now, if you scroll down further, here is where you have the development length for um, deformed bars or deformed wires in tension. So development length. Now, like I said, the bar can be either be subjected to tension, meaning the bar is being pulled out of concrete, or the bar is being pressed into the concrete. Um, development lengths for tension and compression are different, and they have to be calculated differently. So intuitively, development length or the LD value, let's call LD the development length. That is what the code calls. It is a function of um, the strength of concrete, right? And it is the strength of steel. Now, the lambda value, right, which is different if it is a lightweight concrete, if it is a normal weight concrete, etc. It is also a function of your diameter of the bar, obviously, and it is also a function of bunch of modification factors, 2 or 3 different factors. We'll talk about them, but then just for your understanding, when you're looking at development length, you should be uh, these are the primary factors that play into that formula there. We look at it, the exact formula and all that. But what this section here is saying is you calculate your development length based on value from here, and you also calculate. You'll also have to calculate here from here. Let's say the LD is 8 inches, whereas requirement B is 12 inches, right? So you provide the greater, I think, let's go here, the greatest of A and B, greater of A and B. So the max value between 8 and 12, so you go ahead with the development length of 12. Whereas if you calculate the LD value as 16 inches and this is 12 inches, now obviously you're based on this information here, you're providing the development length as 16 inches. So let's take a look at this one and see how we can calculate uh, the development length. So 25.4.2.2 is this table here, and it has, how do you, when you, it has 2 columns and then these rows here, right? So so the columns you enter into this particular table here based on the size of your bar. If you have a number 6 and a smaller, then you get into you get to use the formula in this section here. If you have a number 7 and larger, you get to use this formula here, right? So that's about the columns. Now about the rows, you will have to see where you fit. So before we read through all this, one important information is development length is dependent upon clear spacing. These are the 2 important parameters. There is a, this is the jugglery in the code. Clear spacing, and you will also see clear cover. So if you have a beam like that, let's say you have that from this bar to that bar, that is your clear spacing, and from here to here is your clear cover, right? So you will have to have these values handy before you either get into this or you get into that, correct? So for this section here, if you can read through, let's say you have a beam there, a beam like that, you have your bars like that, right? And your clear spacing between the bars, that is from here to here, that spacing should be greater than dB, right? And then the cover, clear cover, should also be, let's say you have a stirrup here, let's say the clear cover should also be greater than dB. So when that happens, you fit into this section here, and if you are in this column here, if you are in this column here, then you get to use this formula here. Or if you happen to be number 7 and greater, then you get to use this formula here. We'll get into the details, but then that is how you decide which row you fall into, right? So now the second row, for example, this one here, let's say you have beam like that, and you have your reinforcement bars like that, right? You have a the clear cover greater than dB, and the clear spacing between the bars, that is greater than 2 times of dB. 2 times of dB is the diameter of the bar that you want to develop, right? So that's just the diameter of the bar. Um, Now we talked about clear spacing, this word called clear spacing, and we also talked about this word called clear cover, correct? So based on the clear cover, clear spacing, and your situation, your detailing of the beam, and the size of the bar, you will select either one, either two, or three, or four. Clear? Now let's get into this formula here. Let's see what all it contains. Quickly, like I said, development length obviously is a function of the strength of your steel. There are two modification factors. This is called top reinforcement modification factor, and I think this is the coating factor. So these bars, imagine you have a bar, you're trying to hold it with your hand. Okay, so let's draw your hand. Let's say you are trying to hold it with your, imagine this is your nail, holding it with your hand, and let's say I coat the bar with epoxy or some kind of oil, right, to protect the bar from being corroded. People do that in bridges, and I try to pull it. Then the development, because the friction value is now different, it is easier for the bar to slide out. So you need to increase the standard development length by a factor, and that is this factor here, psi e. So psi e is all about the epoxy business or coating business, and psi t is about the location of the reinforcement. Uh, for example, let's say you have your reinforcement here, and the below the reinforcement there is at least 12 inches of concrete. Then what happens is, as during the curing process, water would raise and get accumulated near these interfaces, uh, and the friction between the bar and the concrete at that interface is going to go down. Again, it is similar to a person holding a reinforcement bar with his wrist, right? If you have some moisture between your fingers, and someone is trying to pull the bar away from your hand, then you need more grip, more you want to it's like wanting to have a wider wrist. A friend who has a wider wrist than you can can hold the bar for a little longer, right? So the width of the wrist is like the development length here. If I can, these are funny analogies, but then I'm just trying to um, simplify all this, right? So like I said, T is the top reinforcement factor. Forget about the exact words, but this has to do with the location of the reinforcement. And if you have and the concrete below it, if you have a decent amount of concrete which is greater than 12 inches, then there will be the water will raise up, and then there will be a reduced bond here, and that's why you need to increase your development factor or development length calculated. The basic development length calculated by a, so let's say you calculate LD as 8, and you need to multiply that LD with a psi t factor now. That means that this fellow is usually greater than 1.0, right? So that's about these two factors. Your dB is the diameter of the bar right there. That is the dB that you are trying to develop. This is the strength based on the strength of the concrete. The lambda is, again, if you have a normal weight concrete, NCW, it is 1.0. Lightweight concrete, it's 0.75. You guys know all this, and this is just an empirical constant there. So similarly, so the only thing different between all these things here are the constants, but the concept is all the same. LD is a function of your Fy, all the factors, the diameter of the bar, and also it is inversely proportional to the strength of your concrete there. So that's about this section here, right? Let's scroll down, keep going down. The code also provides a slightly A more general formula. The only thing, couple of things different between this formula and the ones that we already seen. There's a newcomer here. His name is size. That is the size factor, meaning has to do with the size of the diameter of the bar. If you remember here, that was taken care automatically by these different columns here. So in other words, based on the diameter of the bar, you will either get into this or you get into that. And based on the cover and the spacing, you will either get into that or you will either get into this one, and then pick up your appropriate value, right? So this fellow here is again, like I said, development length, bunch of factors. These are the parameters: steel, concrete, all the modification factors. The psi t, which has to do with the position of the reinforcement. Psi e has to do with your epoxy, and psi s has to do with the size of the bar. There's a new. This is a newcomer here, new term. It's called CD, KTR, DB. Again, for the breadth, we don't have to get into the calculation of KTR and all that. I don't think it'll be pretty time consuming and all that. So you can assume, the code itself says you can assume a KTR value of 0. So once the KTR is 0, that term is gone. So you are left with CB by DB. DB, we discussed about it. The DB is the diameter of the bar that you want to develop. CB, the funny part is not defined elsewhere. It's only, you can only find reference to CB or definition of the CB information here, right? Which is in the commentary part of the code. And the CB is has to do with the cover, right? Let's say again you have a beam like that. You have one cover on this side, you have another cover on this side, correct? Cover on that side. But CB is the smallest of two values. It is smallest of number one, the distance measured from the surface of the concrete, that means from here to the center or here. So this is the surface of the concrete, or this is the surface of the concrete, to the center of the bar being developed. Let's say we are talking about development length of this bar. So to the center of the bar. So you find out that distance, you find out this distance, they might be different, right? You find out from here to here, and that is the smaller of those two values. Let's say this is C1, let's say this is this value here is C2. So the number one is minimum of C1 and C2. And you also do you also find out another value, which is you find out the clear spacing, or sorry, the center to center spacing from here to here. Let's say that spacing of the bars that are being developed. Obviously, these are the bars that are being developed. Let's say this is S, and you find out half the value of S. So you compute the minimum value of number one and number two, and that is your CB, right? So what I wish is, I wish code were to have a clean picture like that, saying, okay, if here is the bar, here is the bar, from here to here, that is my S that we're talking about, and from here to here, surface 1 is my C1, and from here to here, my surface 2, C2, minimum of C1 and C2. There might be a technical reason why all the sketches are not in the code, but for a student or for a practicing engineer, might be helpful to have a small sketch. And the intent of all these videos is just to add a little chicken scratch on the code and make it a little more easy to interpret and all that. Okay, so you find your CB value, then you find your DB value. There's a small catch here. This particular value, CB KTR by DB, should not be greater than 2.5. So if you get 3, use a 2.5 there. Now plug and chug, key in all these values here. These values come from a table that we have already seen. You know the CB based on the detailing of the section, geometry related information. You know the diameter of the bar that you are trying to develop. You know the grade of the concrete. You know the lambda value. Find out LD, right? So that's how you find out LD, but then that's not it. You will have to go back here and then compare the calculated value of your LD with A and B. A is your LD value. You also have to see if the you'll have to consider this value and consider the greater of A and B, right? So that's about bars under development length for bars in tension. Now, if you go further, we talked about this, right? I think we talked about this, but let's again, this is where you pick up your constants from, information about the constants, right? One is the epoxy. This is like your the coating on the bar. If you have coating on the bar, depending upon what kind of coating, I don't want to read all these things, or depending upon if it has a coating or not. If there is no coating, you don't have to amplify the development length. If there is some sort of oil, slippery epoxy coating, then you'll have to bump it up. If you have a bad, much more slippery coating, then you'll have to bump up your development length, the LD value by this factor, the basic LD value by this factor, right? Um, and the LD formula already has those factors. You just have to key in to calculate your amplified LD value. Now this one here, size factor based on the just a function of your diameter of your bar. Number 6, you are here. Number 7, you are here. Number 6, you are here. Right, 6 and smaller. Now this one, like I said, based on the position of the reinforcement, you have um, you, you have your bars, and let's say bars are sitting on concrete which is greater than 12 inches, then you get into this category. You amplify because it is losing some friction. You amplify that value a little bit. If you if you are sitting on a shallower surface, you don't have that issue, then you don't have to amplify the basic development length value. So that's about this section of the code, right? Then we can get into other. Let's talk about now. Development length is not only for regular bars; it is also for hooks. Hook is you take a straight bar. Let's say that is a beam. Let's say that is a column. Let's say the column is only 14 inches, right? But then your development length needed is 18 inches beyond the critical section. Again, this is the critical section, let's say, for the moment. Now, how do we can obviously we cannot have the bar sticking out like that, right? So we will have to take the bar, bend it. The bent bar um, this is a 90-degree hook. You can turn it, then it becomes a 180-degree hook and all. So the development length for hooked bars is computed per this section. LD, there is a small h signifying that it is hooked bar. Again, it is a function of Fy. There are a bunch of modification factors, psi e, psi c, psi r, right? And then it is also a function of your lambda, and it's also a function of your strength of concrete, right? Tensile strength of concrete, whatever. And then the diameter of the bar, right? Again, you calculate it for this, then you do that, 3 values, take the greater of A through C, correct? So how do you get these values? Again, everything is here. Code has everything. Just need to broaden your vision and look at the details, and that is just a practice. You'll develop it. Your eye will start to catch those details if you start practicing it. Again, lambda depending upon you are here or here. This value are normal weight concrete. Epoxy coating, which type? Cover, what is the so the cover, it is a nice sketch here. For number 11 bars and smaller hooks with side cover, there is a side cover for a hook, and there is also an end cover for a hook. So if your side cover is greater than that, 2.5, and bar extend beyond the hook, this cover beyond the hook is around is greater than 2, then you use a 0.7. Otherwise, you use 1, right? And then think there's a sketch showing that information somewhere here. Maybe wrong. Okay, anyway. So the only two values. If you have a, you'll have to check um, the side cover and see if it is less than that value there. 1 second here. Um, that number, and then there is a beyond the hook. There is a spacing there. So you have to look at those two details and see if you fall here or if you fall in this category here, right? Now, if you confine if the reinforcement is confined, meaning the bar, here is the bar for which we are calculating obviously the development length, and let's say there are these stirrups which are trying to confine the bar being developed. Then, depending upon the spacing between those bars and the spacing of the first bar from here. So this value and this value, depending upon that value, um, you can take a advantage, meaning you can reduce the development length, right? So sometimes the stirrups run like this, perpendicular to the bar being developed. What they're showing in this sketch here is the stirrups running along the direction that like that. Stirrups are running along that direction. So depending upon the direction of the stirrups, you are either for a 90-degree hook and for a 180-degree hook, number 11 and smaller, you are either here or you are either there. So you find out those three values and get into, and then you find out all these values, then it's a simple plug and check, right? Let's go further. So sometimes here is a beam, and then when the beam has a discontinuous end, meaning there is nothing on this side. So there's a discontinuous end. If there is a, for bars being developed by a standard hook, a discontinuous end of members, which is that particular. If I were to have, sorry, I have nothing here, then it's a discontinuous end. Then based on the cover, if you have a cover less than 2.5 inches on the side and on the top, right? On the side and on the top. If your cover is less than 2.5 inch, then you have all these conditions A through C need to be satisfied, right? Meaning the hooks shall be enclosed for LDH. The hooks have to be enclosed. Enclosed meaning again you need to add stirrups like that, and the stirrups have to have a certain spacing. You cannot put one stirrup, two stirrup, and then call that this is enclosed, right? This is not enclosed. You need to have stirrups at a certain spacing is what they're trying to say here. The first stirrup has to be this detailing information of the first stirrup here, right? And then the psi r shall be taken as 1.0 in calculating LDH. D is the nominal diameter of the hooked bar, which is this particular bar. So the terminology, again, hooked bar, we know what it is. LDH, we know why it is H. We know what S is, the spacing between these reinforcement. We know what confinement means. This bar is being confined by this. It's like putting a person under a prison, right, and closing the prison door. It's like a jail. So you're confining it. We know what this is, we know what that is, we know what psi r is, we know what dB is. So becomes easier to understand what the code is saying there, right? Now let's go to this section here. Let's see what this one is. This is for development length, bars in headed bars, headed deformed bars in tension. So you take a bar, and plain English, you add a head to it, right? So if you're trying to pull this bar versus trying to pull a plain bar, which is inside concrete. This is inside concrete. Assume that this is also inside your concrete beam, right? So these are two cases. Trying to pull this bar is easier compared to trying to pull this bar, because this bar will start to push the concrete, or the concrete will have a reaction on, and it is trying to help the bar from not being pulled out. So obviously, headed bars will have certain advantages, but there are some rules. And first rule is your bar should conform to that particular section. Your yield strength should not, let's say you have 80 psi bar, but you still have to use 60 psi in your calculations. Bar size shall not exceed number 11. Net bearing area ABGR, and you will have to shall be at least 4 times ABG. Whenever people say net, that means you take the entire area of the headed bar and remove this particular thing. So this particular shaded area, hatched area, is the net area. That net area has to be at least 4 times area of the bar. Area of the bar by dB square by 4. dB, the diameter, right? So that means this particular uh, head, now we are looking at this one from this view here. We're looking at it like that. So I'm talking about that head is this head, right? This particular thing has to have a certain area, certain character to it. Otherwise, it's not going to act as it will look like a headed bar, but it will not act like a headed bar, right? So that's about these things. It should be normal weight, shall be treated as normal weight, and shall be at least that much clear cover for the bar. You already know what cover is and what a spacing is. So that's a common pattern here. They are always worried about cover and a spacing. So we are worried about cover, spacing, strength of concrete, yield strength of steel, lambda value, obviously. Then what else? And a bunch of factors. Uh, and if you know how to look for these factors, if you know how to go into different tables to find out these factors, then you can calculate development length pretty easily. So that's about deformed bars. LDT. We talked about these conditions. We did not talk about how the development length of that headed bar, how that LD value, LD, what do you call it? LDT has to be calculated, right? And LDT is from here, but then you will also have to compare with those limits, and you will have to respect this condition, right? And there's nothing new here. There is a epoxy related information, diameter of the bar. This is given here. About the here is the this is based on the concrete, and that particular Fi is based on steel, just an empirical constant, right? So if you know these things, plug and check, find out this, find that, and select the greatest of 3, right? So that's about this section here. Crawling down, so that's the headed bar there, right? You see the head, that's the development length, LDT, critical section, so you need to have that much, right? And again it helps. This is a good picture, I like it. Because we don't have space, I could not do this, because my development length is that much for a normal bar. So what I do is I stop it short and add that plate and see if this much is, calculate my LDT. LDT might pretty well fit within the width of the column. So we are this is a workaround. If you need, maybe the moment is higher, there's a higher demand on the tension, higher tension in these bars. So we need uh, development length greater than the width of the column. We can't do that from the critical section. So we come up with a smart idea of adding a plate, so that the plate, when you try to pull this bar, plate is going to push the concrete. Concrete is going to produce a reaction. So let's say this is the plate. Here is a bar. You pull the concrete, you pull the bar. there's concrete surrounding. Concrete is gonna produce a reaction and hold the bar from not being pulled, right? So I like that sketch there. So we're done with that. There's a lot here, but then I'm just covering information needed for a breadth type of exam, right? Not the depth type. Bars in tension, nothing much here. With the information I gave you, you can easily understand all this. If you have a welded plain bar, how do you calculate your development length, right? And that should be deformed bars in compression. Now, if you have a bar, development bar, if you have a bar that is being subjected to compression, let's say as a concrete, you're trying to push the bar into the concrete. So the compression bar, um, it'll seek help, or it'll get help from concrete because it is bearing against concrete. So the development length in compression will not be a huge value compared to the development length in tension. So the code says LDC compression. The other one was LDT. Again, same pattern. If you look at the bird's eye view, they give you something, they say go here, and they say you compare with the other one and calculate that. You go here, you find a formula. Same pattern here. It depends on the strength of the steel. Your new factor, say R, we'll talk about it. Then empirical constant, the lambda, and the strength of steel, and then you compare that, and you use the greater of A and B. You don't end your story here. You find that and then compare with this, then do the greater. So that means look at the entire section there. Correct? Again, confinement information. You have, let's say your bar might be confined by other bars, and if you have this type of confinement, if you have this type of confinement, if you have that type of confinement, and if you have something like this, you reduce the development. You don't need as much development length. Um, let's say you have an unconfined case, you need X. Then if you have a confining reinforcement around the bar that you are trying to develop, then you need 25%, 75%, or you can reduce 25% there, right? Um, this is again a common thing for development length. So there is AS required and there is AS provided, right? So many times we provide, this is based on calculations. Let's say you want a 3.5 inch square of reinforcement, whereas you are a very conservative engineer, you provide 5-inch square of reinforcement. You can reduce your development length because there is excess steel. Because you are providing 5, not it only needs 3.5. That means your steel is not going to get stressed um, much. So you can reduce the development length LD by this factor. So it is just trying to correct the stresses in the steel, actual stress in steel, yield stress in steel, something like that, right? So it's, and that is true for tension as well as compression. We did not talk about this in the tension case, but then this is how you can reduce or take advantage of the provided steel to come up with a reduced value there. So that's about that, and I think that's about everything. Some basic information about the development length. In summary, LD is a function of bunch of things: strength of concrete, strength of steel, lambda. Then there are a bunch of factors, and those factors depend upon your spacing, your cover in both the directions, and all that. Based on that, you have and if the bar has 12 inches of concrete underneath it, or if there is epoxy coating around the bar, making it slippery and all that. So that's what I wanted to cover. Obviously, we did not cover everything, But if you find it helpful, let me know. If you have any other questions also, let me know. Thank you very much.